SwayamPrabha. Digital India. Educated India.
Hello, welcome back to lecture 9 of Aerospace Structural Analysis. We will continue with the membrane analogy that we started in the last class. So, membrane analogy, as I mentioned, is a technique similar to a technique which can be used to solve the problem of torsion of circular cross section shaft, as we have done using Saint-Venant's theory and Prandtl stress function. So, as I mentioned in the last lecture, if we can imagine or visualize a membrane in the xy plane, a thin membrane with a normal force N acting along the edge or boundary of the membrane and a vertical pressure Q per area acting all over the membrane, then the out of plane deformation of the membrane which is W, which is a function of x and y, is analogous. So, this one is analogous to the stress function phi of a shaft with same cross section. Okay. Let me explain this. So, if we can visualize a membrane whose shape is similar to the shape of the cross section of a shaft which is under torsion. So, let us first understand this point. So, I have two things. I have a membrane which has a certain shape, arbitrary non-circular shape, and I have a shaft which has the same arbitrary non-circular cross section. Now, the out of plane deformation of the membrane under the condition that has been mentioned can be visualized. Let us call it as W. So, this W would be similar or will look same as the Prandtl stress function of the shaft. So, this is a very useful technique, a practically useful technique to find out or estimate the stress function of a shaft with arbitrary cross section. So, let me write it down. So, I have a membrane . I have a shaft under torsion. So, what I have is that I have shape of the membrane is same as shape of the cross section of the shaft. Now, if this is the case, then W, that is out of plane deformation of the membrane, is analogous is equal, or I cannot directly use the term equal, but it is analogous or similar to the stress function x y. Now, how is this useful? We can always visualize a membrane like this. We can visualize the out of plane deformation of the membrane. That is very easy to do. We can easily visualize the out of plane deformation of the membrane. Once we can visualize that, then we can also visualize how will be the shape function of the cross section of the shaft. So, if I find out W, I know what is phi. So, this is very important practically to find out the stress function for cross sections which are very complex, and we cannot use the conventional equation of the Prandtl stress function or the Saint-Venant's theory to find out the expression for phi. Now, our next job is to see why they are analogous. We need to mathematically derive and show that they are analogous. Let us attempt to do that. Let us consider a small elemental area of the membrane which has a dimension of dy and dx. So, I am just considering a small elemental area in the membrane. Now, what I want to do is that I see the force equilibrium of the elemental area. Okay. So, if I draw the free body diagram of the elemental area, so if I draw a portion of the elemental area in the xz plane, so W is this is not the edge, this is not the boundary. So, W is the out of plane deformation at this point 1, and thereby W plus del W by del x into dx is the deformation at point 2. Now, let us try to write down force equilibrium in the z direction. So, I missed writing here in the vertical or z direction. If I write down, then I have minus n dy del W by del x. I am taking the vertical component. I am basically taking this component. So, this component, the total force is going to be n into dy, and the vertical component at point 1 is going to be cos alpha, which is going to be cos alpha, which can be written as del w by del x. Similarly, at point 2, the total force is n into dy, and the component of that would be del w by del x. So, this is one part of the force. The other part of the force from the yz plane can be written as minus n dx So, these are the component of the n force, the boundary force n that is being applied. Apart from that, there would be q, which is acting per unit area, into dx into dy, and this whole thing has to be equal to 0 for the equilibrium condition in the vertical direction. Now, if I simplify this, then I will see that this whole equation, because this cancels out with this cancels out with this. So, the whole equation boils down to n which implies that so this is the equation of W in terms of x and y. Now, let us see this equation, let us note down this equation, and let us remember the equation of the Prandtl stress function. So, if we remember the equation of the Prandtl stress function, it is of this form. Therefore, if minus 2g is, if the forces applied on the membrane, that is q by n, q and n, are such that this is similar to this, then W is going to be equal to phi. Then W, from this whole thing, we can write that W, which is function of x y, is analogous to phi, which is function of x and y. Given that minus q by n is similar to minus 2g theta. Even if they are not similar, the exact values will not be the same, but the shape or the shape, that is W, the variation of W over x and y, will be similar to phi. Maybe the magnitudes will not match, but the shape or distribution will match exactly. Okay. So, this is a great technique, because this is practically very useful, because for certain arbitrary shape it is extremely difficult to find out a Prandtl stress function which is going to be 0 on the boundary, as well as which is going to satisfy this constraint. this constraint. But the deformation of a membrane can be very easily visualized. We all can visualize how the deformation of a membrane will look like, and from that we can imagine or have an estimate of the stress function G. So, this whole thing is called membrane analogy and is a very useful technique. This whole derivation that we have done and this whole concept is called membrane analogy. It is extremely beneficial practically to find out the stress function for a non-circular cross section shaft and solve the torsion problem. It is even more useful when we try to deal with thin wall structures. So, we will see soon that how effective is membrane analogy in the analysis of thin wall structure. Before we move on to that, I want to investigate the membrane analogy further and see if we can utilize it even more. So, let us discuss about certain corollary of membrane analogy. So, let us consider this membrane that we have talked about. Now, if I once I know the W x y of this membrane, or once I visualize either I know it mathematically or I can visualize W x y, then I can also visualize contour line of the inside the member. So, this is contour. These are contour lines for, or let me just use a different color. These are contour lines where W, which is a function of x and y, is constant. Right. So, the usual meaning of contour line, I take the membrane, I draw the lines along which W is constant, or the line connecting the points with constant displacement, which is called the contour line. Now, let us see what is the property of the contour line. So, first let me tell you that the contour lines at any point on the contour lines of the membrane, the shear stress has a 0 resultant in the normal direction and the entire resultant of the shear stress on the point is in the tangential direction. So, let me just put it in another word. Suppose I select a point P on the contour line. Now, at point P, I will have two shear stresses. One would be the tau x z as we have seen earlier, and one will be the tau y z. Now, the beauty is that the resultant of tau x z and tau y z in the direction n, which is, or in the direction of the normal to the contour, okay, the shear resultant in the direction of the contour, let me call it as tau n subscript r is equal to 0. So, the entire resultant will be in the tangential direction. So, tau tangential resultant is only there. Okay. So, suppose I need to find out the shear stress at a point on the cross section of the shaft, then I have to imagine a contour line through the point. Then I can say that the resultant or the total shear stress at the point is only in the direction of the tangent of the contour, and the resultant in the other perpendicular direction is 0. This knowledge is very beneficial, as we will see later when we solve example. So, if I have a shaft with a certain cross section, the cross section is similar to that of the membrane that we have visualized or imagined. Then if I select any point on the cross section of the shaft, then the resultant shear stress at the point is going to be tangential to the contour through the point, right. So, suppose I am given this problem that I have a shaft with a cross section and I have to find out the shear stress at a certain point on the cross section. So, mathematically, by using the Prandtl stress function and all, it could become very complex. Then what I can do is that I can imagine a contour of that assumed membrane through that point P, and the resultant shear stress at the point P is going to be in the direction of the tangent of that contour. So, this might the advantage of this might not be very prominent at this point, but when we solve example we will see that we can use this to bring down our calculation to a large extent. And just by looking at the shape of the cross section and just by imagining an analogous membrane, we can tell what would be the value of the shear stress at that point. Now, let us prove this. Let us prove that it is the resultant of the shear stress is in the tangential direction. Now, for a contour line, the first thing that I need to write down is that on the contour lines of the deformed membrane, del W by del S is going to be 0. W is constant along the contour line, S is the tangential coordinate. So, del W by del S has to be equal to 0. Now, let us find out the resultant of shear stress at any point P on the contour. Either we imagine that the point P is in the contour, or once we know P, let us imagine a contour line through that point. Okay. Now, the resultant of the shear stress, so if this angle is alpha, the angle with the normal to the contour and the x axis, if this is alpha, then the resultant of the shear stress is tau x z into cos alpha plus tau y z into sin alpha. Resultant of the shear stress at any point P in the normal direction. I am trying to find out the resultant. So, this is important. So, in the normal direction, resultant of shear stress at any point P on the normal direction. So, how I can evaluate this, right? It is going to be tau x z into cos alpha plus tau y z into sin alpha. Let us now derive this. From tau x z, from the Prandtl stress function is del phi by del y. Now, cos alpha is going to be dx, dy, and this is ds. Therefore, cos alpha can actually be written as dy by ds from geometry. Cos alpha is going to be dy by ds. Similarly, tau yz can be written as minus del phi by del phi by del x into sin alpha, sorry, this is sin alpha, sin alpha is minus dx by ds. Therefore, this whole thing can be written as d phi by ds, and that has to be equal to 0, because phi is analogous to w. Therefore, del w by del s is analogous to del phi by, instead of normal derivative, let me write this as del phi by del s. Right. So, since phi is analogous to w, del phi by del s is analogous to del w by del s. Now, since del w by del s is 0 on the contour line, del phi by del s is also 0 on contour line. Therefore, the resultant shear stress in the normal direction is going to be 0 at that point. Now, let us find out the resultant shear stress at P in the tangential direction. The same point, the same contour, I am just finding out the resultant in the tangential direction. So, let us write it down. So, that is going to be tau xz minus into sin alpha and plus tau yz into cos alpha. If we look at it into geometry, tau xz in this direction is going to be minus tau xz sin alpha, and tau yz in this direction is going to be tau yz cos alpha. So, we do the same thing. Tau xz can be written as del phi by del y, and tau xz yz is del phi by del x minus. Now, in place of sin alpha, I can write this as dy by dn, where n is the elemental distance in the normal direction, and this can be written as dx by dn. So, this whole together can be written as minus del phi by del n. So, which is analogous to minus del w by del n. So, therefore, the resultant of the shear stress at that point is 0 in the normal direction, it is only there in the tangential direction, and in the tangential direction it is equal to the slope at that of the deformed membrane at that point. This is del w by del n is nothing but the slope of the deformed membrane. Therefore, we can say that the resultant of this is analogous to the slope of the deformed membrane Now, this is also useful to find out the maximum value of the shear stress. So, the maximum value of the shear stress will happen at that point where the deformed membrane has the maximum slope. So, we will understand this even more clearly as we solve more example problem in the next lectures. Thank you.